Hey folks, welcome to your last set of Chemistry 1 video notes for Unit 6. Today we'll be covering what's truly one of my favorite words to say, stoichiometry. This lesson will cover standard C.4.5, which asks you to be able to use a balanced chemical equation to calculate the quantities of reactants needed and products made in a chemical reaction that goes to completion. If I'm being honest, most of this stuff involves skills that you should already have learned from earlier this year. You're just going to use them in a new way, so let's get started. First things first, let's reminisce on a few items. A while ago, we learned that a mole is 6.022 times 10 to the 23 particles. Those particles could be atoms or molecules depending on the substance we're talking about. It's nothing more than a unit. We can use this to convert between moles and particles of a substance by creating a fancy form of 1. If 1 mole equals 6.022 times 10 to the 23 particles, then we can create these two fancy forms of 1. We would then take this and multiply it by some information we're given in a story problem. Whichever unit we start with must be the unit on bottom in the fancy form of 1 so that we cancel out our units and convert to new ones. So if we know we had 10 moles of H2, we'd multiply that by 6.022 times 10 to the 3 particles over 1 mole, so that moles cancels out and we're left with particles. We won't use that conversion nearly as much as we will molar mass. You've learned that to determine the molar mass of a substance, you have to add up the average atomic masses for each of the atoms present in a molecule. For example, H2O has 2 hydrogens and 1 oxygen. So we add up their average atomic masses, the ones we find on the periodic table, and that gives us our molar mass. The unit for molar mass is grams per mole. In other words, 1 mole of that substance weighs that many grams. A fancy form of 1 is a conversion factor. When two values are equal to each other but have different units, we can use them to convert from one to the other. When we do that, we must make sure our units cancel out. We'll see some examples of that today, so sit tight. One of the simplest conversions we can do, and one that involves molar mass, is converting between grams of a substance to moles of that substance, or vice versa. We use the same process we did when we did unit conversions at the beginning of the year. If you know the number of moles, but want to find the number of grams, you'll multiply by the molar mass, putting moles on bottom and grams on top. The moles will cancel out and leave you with grams. If you know the mass but want to convert to moles, you'll divide by the molar mass, which puts grams on bottom and moles on top. This will cancel out the grams and leave you with moles. Notice on both of these conversions we have 1 mole. Molar mass tells us how many grams are in 1 mole. So when we use the molar mass as a conversion factor, the mole side of that fraction will always say 1. Let's go to the board and do a couple examples of those. All right, so our first example of molar mass conversions is to take 36 grams of water and convert to moles of water. Before you can do that, you need to know the molar mass of water. So if we look on our periodic table, we find that hydrogen is 1.008 grams per mole, and oxygen is equal to 15.99 grams per mole. We have 2 hydrogens and 1 oxygen, so we have to add hydrogen twice here. And that gets us a molar mass of 18.015 grams per mole. Now that we know that, we can do our conversion problem. So we start with the number we're given, 36 grams of H2O, multiply by a conversion factor. What this tells us is that there are 18.015 grams in every 1 mole of H2O. So to find our fancy form of 1 here, we can divide either side by that value to get 1. So I want grams on bottom, so I'm going to put my grams on bottom. And now this all equals 1. So I can put 1 mole of H2O is the same as 18.015 grams of H2O. And that's the same thing as just multiplying by 1. It's how we convert our units. So when I do that, my grams of H2O cancels out. I'm left with moles of H2O. I take 36 divided by 18.015, and I get that there are about 2 moles of H2O in 36 grams of water. So our second problem is basically the opposite of our first one. We're given the number of moles and we want to find the number of grams. So first step, figure out what the molar mass of your substance in question is. So we have H2, add up the atomic masses for both of those atoms in H2, and we get that the molar mass, we'll call it big M little m, is equal to 2.016 grams per mole. Now I just plug it into the conversion problem. So if I have 15 moles of H2, multiply that, I want moles of H2 on bottom, which means I'm going to have grams of H2 on top. For every 1 mole of H2, we have 2.016 grams. When we multiply that, we get about 30.032 grams of H2. In other words, in 15 moles of H2, we have 30.032 grams. Unfortunately, the molar mass only lets us convert between grams and moles of one substance. If we want to get from one substance to another one, we have to use a balanced chemical equation that involves both of those substances. Since our balanced chemical equation is like a recipe, we can use the coefficients in front of each formula to convert from molecules or moles of one substance to a different substance. For example, in the synthesis of water, we use 2 moles of hydrogen for every 1 mole of oxygen to produce 2 moles of water. Each of these values is equal to each other, so we can use them as fancy forms of 1. Let's go do some examples of that. Okay, so to convert from one substance to another, we have to use a balanced chemical equation. It's very important that that equation is balanced because that tells you the ratio of all of your substances when they undergo that reaction. So if we want to know how many moles of water, according to this equation, we would produce by consuming or using 16 moles of O2, here's how we do that. Start with what we know, just like any conversion problem, 16 moles of O2. And then our fancy form of 1 here is based on the coefficients and what units we need where. So if I have moles of O2 on top over here, I need moles of O2 on bottom, on this side. And I want to convert to H2O, so I want moles of H2O on top. According to our equation, for every 1 mole of O2, because remember, a blank space before a coefficient is just 1. For every 1 mole of O2 we use, we produce 2 moles of H2O. And now we just multiply the tops and divide by the bottoms. So 16 times 2 is 32. We would make 32 moles of H2O with that amount of oxygen. Okay, a similar but different problem would be if I want to make 42 moles of H2O, how many moles of hydrogen do I need to react with oxygen? Do that the same way you did the last one. So we start with what we know, 42 moles of H2O times, use the coefficients from our equation. We want moles of H2O on bottom, and our equation says there are 2 moles of H2O. And we're looking for moles of H2, so that'll be up top. And according to our equation, there's also 2 moles of H2 needed. So if we take 42 times 2 divided by 2, we get 42 moles of H2. When we measure out substances in the lab, we tend to use balances that measure in grams. As far as I'm aware, there are no balances that measure in units of moles. Since the only way to get from one substance to another via unit conversions is by converting moles of one to moles of another, using the coefficients from the balanced chemical equation, there is no way to convert directly from grams of one substance to grams of another. This is where my favorite word, stoichiometry, comes in place. Stoichiometry is measurement and conversion of quantities of substances in a chemical reaction. So if we want to get from grams of one substance, say substance A, to grams of another, perhaps substance B, we have to use a three-step conversion using the two conversions we just learned. So if you're given grams of A, you've got to convert that to moles of A first. Do that by dividing by the molar mass of A, and this will put our current units to moles of A. Based on our balanced chemical equation, we can use the ratio of coefficients from A to B to convert to moles of B. Now that we know how many moles of B we have, we can multiply by its molar mass to get grams of B. That probably sounds extremely confusing, but look at the units on my example here. Each step cancels out the units of the previous step and gives us a new unit on top. So to get from grams of one substance to grams of another, we simply use our molar masses and balanced chemical equation to cancel out units until we get the right unit we're looking for. Let's go do an example of that. All right, here we go. Let's put it all together. If I want to know how many grams of carbon dioxide are going to be produced according to this reaction, if we completely react 130.19 grams of C2H4, we've got to go through a couple of steps. First step is you need to figure out the molar mass of C2H4 and CO2. The molar mass for C2H4 is 26.038 grams per mole, and CO2 is 44.01 grams per mole. So start with what we know. We're going to start with 130.19 grams of C2H4. Our first step to doing these is to convert from grams of C2H4 to moles of C2H4. So we want grams on bottom and moles on top. According to our molar mass, which is what we use for this first step, there are 26.038 grams for every 1 mole. Now that we've canceled out the grams, we're left with moles of C2H4. We want to get to CO2. So we have to use our balanced chemical equation and the coefficients there to get from moles of CO2 or C2H4 to moles of CO2. According to our equation, there is 1 mole of C2H4 for every 2 moles of CO2. Our last step is to convert our moles of CO2 to grams of CO2. So for every 1 mole of CO2, according to our molar mass, there are 44.01 grams of CO2. If we multiply all the tops and divide by all the bottoms, on your calculator you'll take 130.19 times 2 times 44.01 divided by 26.038. Notice I skipped all of those ones because ones don't actually change the value we're looking at. When you do that, you get that we produce 440.1 grams of CO2 when we fully react 130.19 grams of C2H4. Limiting reactants sound like a very concrete and defining title for a reactant. It's not. Let's think back to when we first started learning about balanced equations. You've probably heard a few times, and I know you've heard it from me, that a balanced chemical equation is like a recipe. The limiting reactant is solely based on how much of each of your ingredients you have and which one you'll run out of first. So if my recipe for sandwiches say that I put 2 slices of bread with 2 slices of ham and 1 slice of cheese to make 1 sandwich, and I know that I have 24 slices of bread available, along with 30 slices of ham and 10 slices of cheese, which of those ingredients would be my limiting reactant? Well, let's think about how many sandwiches I'd make if I used up each of those ingredients. If I use all of my bread, since it takes 2 slices of bread and I have 24 slices, I could make 12 sandwiches. If I used all of my ham, since it takes 2 slices of ham and I have 30 slices, I could make 15 sandwiches. If I use all of my cheese, since I have 10 slices of cheese, and it only takes 1 for each sandwich, I could make 10 sandwiches. So if I make these sandwiches one at a time, after I make the 10th sandwich, I'm out of cheese. I've got some leftover ham and leftover bread, so in this scenario, my cheese would be the limiting reactant, because that's what I run out of first. In terms of actual chemical equations, we basically do the same thing. For the synthesis of water, if I had 8 moles of hydrogen and 6 moles of oxygen, how much water could I make? If I use all of the hydrogen, I'd complete 4 reactions, creating 8 moles of water. If I use all of the oxygen, I'd complete 6 reactions, creating 12 moles of water. So after I've done that reaction 4 times, I've created 8 moles of water. And I've run out of hydrogen. This would make my hydrogen my limiting reactant. Let's go do an example of that on the board. All right, for our limiting reactant problem, it's really no different than the one we just did before, except now you have to do it twice because you want to see which one of these, if they completely react, will produce less H2O. So in other words, if we mix these two together, which one's going to run out first? So to do that, we literally just do the same problem we did before, but we do it twice, so one for each of our values here. In order to do that, we have to know our molar masses. So molar masses of H2 is 2.016 grams per mole, and O2 is 31.998 grams per mole. First step here is to convert from grams to moles. So for every 2.016 grams of H2, we have 1 mole of H2. And then convert from moles of H2 to moles of H2O. That'll tell us how much we produce. For every 2 moles of H2, we have 2 moles of H2O. So when we multiply 32.2 times 2 divided by 2.016 and then divided by 2, we get 16 moles of H2O produced. So what that means is if I had an infinite amount of O2, just don't even worry about how much O2 we have. If I completely use 32.26 grams of H2, I'm going to make 16 moles of water. We've got to compare that now to how much water we make with the O2 that we have. So do the same thing. If you have 128 grams of O2, convert that grams to moles. There are 31.998 grams of O2 for every 1 mole of O2. Convert the moles of O2, which is 1 according to our equation, to moles of H2O, which is 2. So now we take 128 divided by 31.998 times 2. And that gets us 8 moles of H2O. So if we were to do this reaction with these amounts of H2 and O2, once we get to 8 moles of H2O, we've run out of oxygen. We're done. There's not going to be any more reaction happen, even though we have extra H2. That means that oxygen here is our limiting reactant. Last but certainly not least today is percent yield. The percent yield will tell us how well we performed a reaction. To find the percent yield, you first need to run the reaction and measure out how much of the substance you actually produced. This is what we call your actual yield. Then, based on how much of your reactants you put together to start with, use the stoichiometric calculations we just learned about to determine how much you should have produced. This is your theoretical yield, because theoretically that's how much you should have made. Finally, you divide the actual yield by the theoretical yield, in other words, what you made divided by what you should have made, and then multiply by 100%. The higher percent yield you have, the better your reaction went. Well, that's it for today, folks. I hope you were able to learn a bit about stoichiometric calculations, and I hope we did enough examples for you to be able to do these when we start practicing them. As always, if you have any questions, let me know.